everyone. I think, sorry a bit for the overtime. I think we are continuing right away. So this is the second to last talk of this day. So we're all a bit tired. This should be somewhat funny, I hope. And also, if you have seen the excellent keynote by William this morning, then you should already be sold on why event time and windowing and why this stuff is necessary. So this is mostly, I'm trying to re-motivate it with my own examples and then give you some details of how it works in Flink. But it's a very short talk, so if you're interested in how it really works in depth, then please come to me after the talk. So basically it's notions of time, so this would be processing time and event time and how Flink deals with this and Windows. And this one's not working. The unofficial title is Adventures in Time Space, so maybe at the end you will get the inside joke in this. So bear with me with this. So the first question is, in streaming, why do you want Windows? And I'm not talking about Microsoft Windows because nobody does that in any real processing, but why do you need Windows? The reason is that you have an infinite stream of data, and if you want to do any meaningful aggregations on this data or computations, you sometimes, you're this dog, the data just keeps arriving, and to deal with this data, you have to split the data into buckets. So in batch, what happens is you have the data sitting on disk somewhere, the data is done, data is finished, no new data arrives, then you start a batch job on Flink, for example, then this produces some result, and then you're done. In streaming, you have data arriving continuously, you have your Flink job running continuously, and you have your results continuously. So the first thing that you should remember from this talk is the most important concept in streaming is data never stops, and you have to somehow deal with this. And the solution, as I mentioned, is you put these elements into buckets, and these buckets are what we call windows. So for example, windows of 5 minutes, or 10 minutes, or a day, or 2 days, or a week, any notion that you can use to split the incoming elements into buckets. So let's motivate this with an example. So let's say you have some data source from which you get tweets. There's, for example, one tweet, wow, just saw Trump on CNN, super cool. And then what you want to do is you want to run a window operation where you basically say over the last 5 minutes of tweets, count me the number of hashtags. And then the result from this computation would be, for example, Trump got mentioned 2,394 times. Cheese is very popular these days, so cheese got mentioned a lot. And some people are also interested in money, of course, as always. But the thing I didn't mention in this example is that tweets, they also have an inherent timestamp. So the time when this tweet actually was tweeted by the person tweeting the tweet. Tweet. And this timestamp is basically what we call the event time of the event that we are processing. And due to the distributed nature of the whole system and of the world in total and so on, you have your processing running somewhere in a data center, and the tweets from all around the world, from all these different users, they arrive with different amounts of delay. And due to this, the tweets arrive at your machine not in the order of their timestamps, but as William, he had a very good picture for this, showed, they arrive basically in an arbitrary order and not in the order of event time, as you would maybe hope to have an easy way of computing this stuff. So let's look at the example again. So maybe this works. Yes. So before I just showed you this tweet, but as I mentioned, the tweet actually has a timestamp at which this tweet happens. And inside this window operation, what you actually do is to form these buckets of elements, these windows, what you do is to take the actual or the current processing time of the machine when the processing is taking place. And the last bit of important information for this is, you know, due to some calculations that you did and some tests, that this Twitter data source actually produces the elements with 3 minutes of slack. And what I mean here is basically that once you get an element, you know that after 3 minutes, no element with an older timestamp can arrive. So basically, the elements arrive with delay and out of order at your window processing operation, but they don't arrive more out of order than 3 minutes. And so what happens now is that, you know, they have 3 minutes slack, but if you take the current processing time of the machine, when you calculate these windows, the results that you compute and that you get here, they don't really match the actual time that is inherent in these tweets, the event time of these tweets, the timestamp of these tweets. So processing time is not event time. That's an important takeaway from this. So you might ask yourself why people do this processing time windowing. And the reason is it's easy to implement. You just have your clock on your machine. Boom, every 5 minutes you process your window, and that's easy. It's also low latency because you know that after 5 minutes you do your computation, you get your result, you don't have to wait or anything. And another reason why people do this is actually because they don't have many options to do other stuff. So this processing time windowing is actually what systems such as Spark Streaming, Apex, Samza, Storm, you have to do it yourself there, what they give you. They don't give you another way of doing, of dealing with time and windows. And of course, you should know by now, Google Cloud Dataflow is not one of these systems. So Google Cloud Dataflow provides a good way of dealing with event time and slack and delays and all this kind of stuff. So let's look at another example to see why, or to further motivate the need for these event time timestamps. So in this example, we again have our tweet source from somewhere, and we know that the elements, they arrive with a slack of 3 minutes. And then what we also have is a data source that gives us a stream of news items. So on websites such as CNN or TV shows on the TV or on Facebook, whatever. So you have some source of news. And these news, they also have a timestamp. For example, here, Donald Trump speaks at a cheese conference, which would be very interesting for a lot of people. And you know that these events, due to some reason, again, global delays, the global nature of the system and everything, they arrive with 8 minutes of slack. So now if you would do your windowing computation based on the processing time of this machine, the elements that you would be processing would be completely unrelated to the timestamps, because what you would ideally do is, in this window operator, you wait. Basically, in this example, you have to wait 8 minutes, because then you can be sure that all the elements that for a certain window of event time would be arriving at your computation. So again, processing time is not event time, and you need some way of dealing with this. Now, yeah, just because it's nice. It's basically a mismatch in the time-space continuum. Because processing time is one axis and event time is another axis, and it's important to understand and to deal with this fact that they don't necessarily correlate. So as I mentioned, some use cases where you might want to use this event time windowing is, of course, the elements arrive out of order. You want to deal with this. Sources that have delay, as I showed in this example where you want to correlate the Twitter stream and these news streams that arrive with delay. Also, you don't initially think about this, but if you have, for example, recovery and fault tolerance, and for example, your streaming computation fails, and it takes some time for the machines to come up again, and then if you just continue doing your processing time windows, then you would be completely out of sync with the time that is inherent in the input stream. But if you have this event time, then it would just start working again and work on this clock of this event time in the elements. This is basically what I'm trying to say here by catching up with the stream. So if you have some data lying around in the stream and your computation stops for some reason and then it re-continues, then it should still be correct and work on the inherent time of the events. And who does this? Google Cloud Dataflow obviously can deal with this, and to my knowledge, the only open source system that can do this is Apache Flink. The others might try to catch up with this, but right now, that's the situation. And now, I want to very quickly sketch how it works to work, that we can deal with these watermarks and these delays and so on. So, the basic idea, what we would need in such a system that can deal with this event time is to have a global, basically a notion of a global clock that runs on this event time and not on the processing time. This is an abstract concept, I admit, but we look at an example of basically how you can keep the machines that are doing the processing in step with the event time instead of the processing time. So this is, for example, an instantiation or a topology of this earlier example. So we have a data source that gives us these news items. We have our Twitter source that gives us the tweets. This is basically the machine that pulls these two streams together. And we have, on this machine, we have our window operator running. That does the actual window computation. And these green bubbles you see, they would be the event time or the current position in the event time continuum as this machine sees it. And what now needs to happen is basically the sources, they know, or they should know, or should have some heuristic of what the delay is in there, and then the sources can update their global time, and then this update of the global time at the sources should propagate throughout the system so that the system has a consistent view of where we are in the event time space. So how this works is, let's say this Twitter source knows that it has seen all the elements for timestamp 0, and then it updates its view of this global time to timestamp 1. And then what it does is it would emit this blue bubble. This is what we call a watermark, and this watermark is sent to downstream operations to notify them that no elements earlier than this watermark can arrive from this source in the future. So it sends this watermark. And now what this operation does, it cannot just update its own view of the clock, but it has to wait for clock updates from all the upstream operations from which elements can arrive. So it would recognize that it has this update from this operation, but then do nothing. But then, if this source then knows, oh, I know my elements, there won't be any new more elements coming for this timestamp, then I can send an update downstream, which is 2 in this case. It sends it to the next operation. And this one now knows I have seen an update for timestamp 1 from the Twitter source, and I have seen an update from timestamp 2 from my news source, so I know I can safely increase my view of the global clock to 1, because no more elements for 1 can arrive from the upstream operations. And then because this updated its view of the clock, it will send its own watermark downstream, and then this operation can update its view of the global clock. And then based on the updates in this global clock, you would actually get the evaluations of these time windows in this window operation. And then let's say this source updates to timestamp 2, sends the watermark downstream. This updates, also sends it. This updates. And in this way, we have a global view of the time that is inherent in the events that we are actually consuming. And they are updated using this concept called watermarks. So now you might be interested in how easy it is to use this. William showed a lot of the Google Dataflow API, so I'm going to show some examples of the Flink API, how it can handle this. So this is basically the example of the the first Twitter example where we just want to count the hashtags. So the interesting bit to note here is that we set the time characteristic to processing time, meaning we want to have processing time windows. Then here we create our data source, that is a Twitter source that reads some elements and creates us a data stream. Then we have some operations, so this one extracts the hashtag. Then we group the elements by the name of this hashtag. It's basically a word count for hashtags. Then we say we want a time window of 5 minutes. And then to this we apply a window function, which is in our case a hashtag counter, which then counts these hashtags in this window of 5 minutes. So this gives you processing time, which, as I showed you, can be incorrect if your sources, they have out of order elements and they have delay and so on. So what you then would want to do is change to event time. And here actually only the blue text is what has changed from the previous example. So none of the operations, so where we extract the hashtag, where we define the window, where we apply the window function that does the actual computation, they have not changed. The only thing that changed is we set the time characteristic to event time, and we need to somehow tell the system how we can assign timestamps to our elements. So in Flink, all the elements, so such as the tweet elements in the stream, they implicitly also have a timestamp attached to them, and using this operation, we can update this internal timestamp. And then this operation would also, this timestamp extractor would also define the way, basically how these watermarks can be computed and how they can be updated. So, TLDL, I'm trying to coin it, too long didn't listen. Basically, the only thing you should remember from this is that stream data is infinite. If you want to compute aggregations on stream windows, on these streams, you need windows. They're helpful for this. The most important bit is that event time is not processing time, and you need to have some way of dealing with this if you want to have correct results. Flink and also Google Dataflow uses watermarks for this, and the most important bit is Flink can actually do it as the only open source system. That's the last slide, so thanks for the attention. I think I actually managed to stay somewhat within time, so we have time for questions now. Do you do the mic?
So I was pretty excited about this, so I looked through the new API this morning.
Mm-hmm.
And I'm wondering if you have any plans or you've thought about allowing the source
Mm-hmm.
to sort of more flexibly define what the watermark is.
Mm-hmm. So there's actually a way, so the normal way that you define a Flink source is that there's this interface source function, and there sources can basically emit elements. But there's also another interface called event time source function, and there the source can emit elements and attach timestamps to them, and the source can also manually update this watermark information, which is then used by Flink to update the watermarks.
If I understood you correctly, you cannot deal with out-of-order events in terms of the event timestamp, right?
No, Flink can.
Also in terms of the event timestamp, because
Yeah, only
isn't
in
the watermark already triggered if afterwards an event comes with a later timestamp?
Mm-hmm. Oh, okay, so you're referring, yes, so the watermark should be close to correct, yes. So basically you have your windows, you put them, basically you buffer them somewhere, and then when the watermark arrives, this tells you that you cannot receive elements with a previous timestamp, and then you process the windows that basically are before this watermark. But then sometimes the watermark is just a heuristic, and it can be wrong, and then you need some way of dealing with these late elements that arrive behind the watermark. And right now there is, it's a bit tricky. So what you can do is basically you emit the window again with this additional update that arrived late, or you can, for example, emit the window as usual and then remove all the elements, and then when the late element arrives, emit this element as a late window result. So that's up to the user how he wants to deal with these late elements, but there's still some rough edges. there in the understanding of users and also how it can be implemented. But that's a good question. That's something that needs to be done. Some way of dealing with late elements if the watermarks are not correct. Want there more questions? The mic man.
I think that last part's sort of important, that it be explicit in the API. That you have a way to say when this happens, because it will, with what?
Yes, yeah, that's something we have to figure out how to basically expose this to the user in a good way. But this we haven't done yet. That's still some work in progress. Yes, please?
Yeah, my question is, with the event time processing, I imagine that it is implemented by using some buffers. And my first question, whether it is configurable. My second question, I think it introduces some overhead. How big the overhead of using event time processing?
So okay, so it depends, as always, on the use case. So for example, if you, of course there's some overhead, because basically what you have to do, you have to keep the windows around until you receive a watermark that tells you that you can process these windows. And if the watermark is very far behind the elements that are arriving, then of course you have to keep a lot of data around and wait for the watermark. That's just a fact that you have to deal with. And another thing, if you are doing associative, commutative aggregations on these windows, then the state that you have to keep around is very small. So if you just want to keep the sum or the count of something, then this is just one value which doesn't, the size doesn't increase with the size of the window. But if you, inside your window processing function, you need access to all the elements that arrived in this window, then yes, the buffers become very big. And then right now, as in Google Dataflow, I think the window buffers are kept on a JVM heap, and basically if your window buffers get too big, then the JVM blows and doesn't work. But we have plans for this to actually use the serialized data and memory management facilities of Flink to put these windows into our managed memory stuff and also spill them to disk if they grow too big. So this would then allow you to, say, have windows that span days or weeks and have them in a fault-tolerant way and in a memory-safe way. But this is not yet implemented, I'm afraid. This is the first implementation of this.
I have one question. Is this feature about watermarks already available in the .9, or it's going to be in the 0.10?
I forgot to mention this, yes. It's actually not in the 09, but it's in the 010, which should hopefully be released in 2 weeks, maybe 3 weeks tops. It's until the community can figure out the last bugs and decide what we want to have in the release or not. But this is already in the release, so if you want to play around with the 010 snapshot version, there's also documentation on the website for 010 snapshot, then you can actually play around with these timestamp windows. And I think yesterday was a talk from Ericsson about also doing event time-based windows, and they were actually playing around with this 010 snapshot version for this. So very last minute, but apparently it worked for them. So that looks good. I'm quite confident there. So.
Okay, I
Yes,
have a
please?
question. What happens when a node crashes? So does that have any impact on the correctness of the results? Or how do you handle that?
Mm-hmm. So basically that's related to Till's talk earlier. So Till talked about the way in which Flink provides fault tolerance by having these checkpoints and then continuously checkpointing the data. And this window data is then also, so this is not implemented right now, this is implemented next week, hopefully. This window data is then also part of the checkpoint, and then when the Flink checkpointing mechanism works correctly, I hope it does, Till, then also the window processing and all this logic uses the same system to keep it fault tolerant and can recover from failures. Yes.
I have other question. It's about the timestamp.
Yes.
Is it a logical one, or is it instead a real date time? And what is the granularity? I mean, it comes to seconds, milliseconds of coordination.
So internally in Flink, it's a long, which is Unix timestamp, basically time from epoch. That's what it is. But if the system would like to use some, or if the user would like to use this as a logical timestamp, he can also just implement a custom source that basically emits watermarks that maybe start from 1 and then watermark 0, watermark 1, watermark 2, and then also assign these timestamps 1, 2, 3 to his elements. Then this would also work because it's transparent to the system what the timestamps actually are. It's just long value. So you could, in theory, implement other stuff, but mostly you would treat it as a Unix timestamp value.
Other questions? Still have time.
I'm around later, so if you find some questions, then you can ask me directly.
Thank you.
Thanks.